Hey guys, how's it going? Today we're going to be learning about electron configuration. I'll go over a brief overview of what this actually is, and we can go over a couple of the principles and rules that are involved with this, and I'll go more in depth on those rules and follow with some examples on how to do the actual electron configuration based on the periodic table later. So let's just start off by saying, what is it? So it tells us how electrons fill the orbitals around an atom's nucleus. Pretty simple. Then you have what you actually need to know. The first is the Aufbau principle. This just says electrons fill the lowest energy orbitals before moving up. I have a diagonal chart on the next page that I'll show you if you stick around, and that's a must know. Hund's rules is within a set of orbitals, electrons spread out before pairing with one another. I'll go more in depth on that. And then Pauli exclusion principle just says no two electrons can have the same four quantum numbers. So let's just start off with the Aufbau principle. So like I said before, it's a diagonal chart, right? So we have kind of just showing, okay, how do the electrons fill each orbital and in what order? So we start with 1s, then we just move to 2s, 2p, 3s, 3p, 4s, and then so on and so forth. Just kind of following that arrow. And that'll become really important when we do it with actual elements on the periodic table, which I have an orbital map of the periodic table down in the bottom left. Both of these images are a must know, and they'll really help on your tests. And then moving on, so we have the Hund's rule right here. So this is just saying, okay, electrons fill a subshell singly before forming any pairs, and each electron in a single occupied orbital has the same spin. So it's saying, so like these bottom two examples that are wrong. So right here, 1s and 2s are the same as the top one. But when you move to 2p, this middle one right here, it says, okay, we have a box here. We have three boxes, right? I'm just showing like, okay, how do the electrons fill the orbitals? But this first one filled two electrons in its first orbital without first filling this without first filling this box. And you have to have a single arrow going up before you can fill the other boxes. Or you have to have a single arrow going up in all the boxes before you have an electron spinning downwards. On the bottom one, the reason that this one's wrong is because all the electron spins are not in the same direction. You have one going up in the first box, one going down in the second, and then one going up. But in the top one, we have three boxes, each with its electron going in the same direction or having the same spin, and then the later ones will have spins that go down like this. And it'll fill up just like I did, 1, 2, 1, 2, 3. So that's just the Hund's rule, pretty simple. And then moving on to Pauli exclusion principle, it says no two electrons can have the same quantum numbers. Basically just saying within an orbital or a set box, right, with 1s and 2s, they have to be going opposite directions. So this goes up and this one goes down. And then in this 2s one, this one goes up and this one goes down. But in this one right here, you have these both going up and then these ones both go down. But they have to be in opposite directions within each box. And there's only two electrons per orbital, or per box of orbital, if that makes sense. All right, now let's put it all together. I would highly recommend having a periodic table on you while you do this, as this will help you just try and put the electron configuration together and you can visually see it. Example 1 says, write the electron configuration of carbon with an atomic number 6. So start with hydrogen and say, okay, this is 1s1. Helium, on the other hand, is 1s2 because it fills the second orbital, right? And then we'll move to this 2s orbital. We'll say, okay, lithium fills 2s1, and then beryllium fills 2s2. Moving across like this, these are all p orbitals, right? These are the d orbitals, and then these are the s orbitals, right? Pretty simple. And then these right here are the f orbitals. So let me erase this really fast. And then essentially what we're going to do is we're going to say, okay, so right now we have 1s2, 2s2, because it's filled all those orbitals, and then we move to boron, which is going to be 2p1, and then carbon is 2p2. So it's going to be 1s2, 2s2, 2p2, and that's it. That's all you have to do. Just put it like this, and that's going to be your answer for carbon. So 1s2, 2s2, 2p2. Very simple. And then moving on to example 2, write the electron configuration of iron. So once again, we can just erase this really fast and say, okay, we started with hydrogen, and that was 1s2, and then helium was, that was 1s1, helium was 1s2. So we'll write 1s2, and we can just cross out lithium and beryllium, and that was 2s2. Because we know iron is going to be Fe26, we'll just move pretty fast. And then this whole row is going to be 2p6, because we fill all these electron orbitals as we're making our way down. because we went through boron, carbon, nitrogen, oxygen, fluoride, and neon, right? Or sorry, fluorine and neon. And then we move to this third row, third group, and we say, okay, we have sodium and magnesium. That's just going to be 3s2. And then we move on to aluminum, and we say, okay, this whole row is going to be 3p6. And then we have potassium right here, number 19, and we know that's going to be 4s2. And then we have the d orbitals now, and we'll say, okay, Fe is 26, so we have 1, 2, 3, 4, 5, 6. And we say that fills 3d6, 6d orbitals, okay? And that's literally just going to be your answer for iron. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And I'll show you a little trick, if you stay for a little bit longer in the video, on how you can make this way simpler and you don't have to write all of this out. So this next one is the special rules. So this is called the noble gas shortcut. This is the special trick I was talking about. So for example, we have, what is the electron configuration of sodium with an atomic number of an 11? So let's go back to our periodic table really quick and look where sodium is. So it's right here, group 3. So we can do 1s2, right? And then we have this second group, which is going to be 2s2, 2p6. And then we have sodium right there. So we know it's going to be 1s2, 2s2, 2p6, and then it would be 3s1, right? But rather than writing this whole thing right here, you can instead look at the noble gas that came before this group 3 and say, okay, that was neon. So we simply say neon in parentheses and put 1s2, or we don't, we put 3s1, and that's it. That's your entire answer, because neon is essentially just covering, it's like neon is equal to 1s2, 2s2, 2p6, right? And then if you wanted to do it for an element that was farther down the periodic table, for example, potassium, instead of using neon, which was the previous one, you would use argon, which is the previous one to potassium. And argon would cover all the ones before potassium. So you'd simply just put AR in these brackets, and then potassium would just be 4s, or sorry, not 4s, it would be 3s, because you have 1s1, 2s, oh yeah, so it would be 4s1, simply just like that, right? Because argon is equal to all of the ones that neon has and more, because you have sodium, which would be 3s2, and then you'd have all those which go across the periodic table, so that would be 3p6, and then that's what it's all covering. So similar to neon, but it just covers all of those, right? So it covers even more. And that's a little shortcut you can do. And then some common exceptions for these rules. So let's start with copper. So Cu, right? So the predicted electron configuration is 3d9, 4s2, right? So essentially what we're saying is, let's look for copper really quickly. It's right here. We'd say, okay, we can, they're just using argon right here, right? Just as a little shortcut. And you'd say, okay, we're filling the 4s2 orbital, which is right here. And then we're going across and saying these are 3d9, right? So, because it's 9 elements across. 1, 2, 3, 4, 5, 6, 7, 8, 9. So yes, 4s2, 3d9, right? Which is the predicted electron configuration. But the d orbital is more stable. You're always looking for stability within chemistry. And the d orbital is more stable with 10 electrons rather than having the 4s orbital filled with 2 electrons. So that's why it kind of takes the electron from the 4s2 orbital and adds it onto the 3d9 orbital, making that 3d10. And the same is true for all of these. It does the same similar idea in silver. It takes the electron from the 5s orbital and adds it onto the 4d9 orbital, making that 4d10. And that's just the special rules kind of explained for electron configuration. And yeah, so that's it for today, guys. Pretty simple, a little complex, but once you get the hang of it, it's not too hard at all. I'll be going more in depth on kind of like electron configuration exceptions, and even more in depth on more examples that are even harder than these, just for common elements on the periodic table. But once you kind of understand one, you'll understand all of them, and you'll have it from there. So shouldn't be any issues. But yeah, that's going to be it for today, guys. I hope you have a great rest of your day. And go ahead and like and subscribe and comment if you got all the examples right. But yeah, have a good rest of your day, guys. Bye.